el caché de mi error. Yep. A ver cómo hacemos esto. Vale. Pues nada, como estamos en un cine...
Okay, since this is a cinema, let me show you that picture on Walt Disney. I'm PEPE VILA. I'll tell you about a project where I've been doing some research with my PhD thesis director. I'm a PhD student at Indea Software, which is an institute here in Pozuela. That's my Twitter account and my URL, where there is a draft of this paper with a little more detail. So I'll do my best to speed up, because I'll tell you about many things. So before I start, Chrome was a black box for me until recently. It renders things with HTML. So here are this is a good list of things where you could start. There are several alternatives like dev lists, where you can actually ask questions. You can talk to developers. If you're interested in a specific functionality, you can find things, pointers and references about code in dev lists. That can be quite useful. Design documents. These are Google Docs used by developers for the Chrome project, with diagrams, potential designs of new functionalities. Most will be out of date, or since they're implementing 24/7, it's a terrible way to do things. When they implement something, it will probably be very different from what you read about in the design document, but to give you an idea, it should be handy. Bug track, well, the same story. You can search for specific functionalities or bugs in functionalities, and there are always references to the code to know where to move around. And finally, if you don't want to install anything locally, this URL gives you all the source code for Chrome with references of different sorts, so it's quite handy to browse. I'm going to be touching on many different things very quickly. If you really want to go into detail, come over and let me know. So, a brief introduction. Event-driven programming, event loops, and the timing side channel on event loops. This is what we will see, a very simple idea in Chrome. EDP is a programming paradigm for GUIs, basically, for web clients. In fact, the standard itself for HTML5 says that you should use EDP. And we're talking about software and hardware, network software and hardware, which is getting non-synchronous packages. So this is a way to program these devices. Also for the server side, it's working quite well on the server side. Java, Python, there's all sorts of frameworks where you can use event loops. The main benefit is that throughput is quite reasonable with very little consumption. The flow of the program is actually determined by the events or the messages that we get. In a conventional program, we would have a main, then a function, ifs, and that would define the flow, the execution flow. With an event-driven program, we define what events we're interested in and what we do when we get them. So whenever we get an event from outside, it could be hardware interruptions or network messages, that would trigger the function we're interested in, okay? So it is widely used. The idea about event loops, very simple. Here we have a FIFO queue and a dispatcher, and then we have a very simple loop we're talking about messages or events. They get to they get here, and the first one in is processed. The important thing here is that when processing a message, if you make a blocking call, like for example accessing the hard drive, data, or the network, it handles it in a non-synchronous way. It processes the event, it delegates the task to a worker that can be another computer, another process, another thread, and that way it keeps processing the other events coming in, or whatever comes from the other clients. That is what makes throughput quite reasonable. So with that very simple idea, we have a concurrency model, which is very simple for the developer, because they may get away from other tasks. But what happens when this event loop is shared between different parties, between mutually distrusting programs? In this case, we have an attacker sending messages or tasks to this event loop, and is measuring the time that each one takes to be processed. So we measure the time between two consecutive events, and we see what delay we have. If we see a bigger delay, we may infer that a victim called V has sent a message, or that it is processing a message not from us, from someone else. So keep that idea in your mind, because this is what we will be using in Chrome to do some cool things. Well, Loophole is the name of the project anyway. Why Chrome? Well, I chose Chrome because it is the most widely used browser. A lot of people say that it is the safest. Some argue that it might be Microsoft Edge, but it is the first multiprocess browser anyway. Other browsers are catching up, I have to say, of course. I'll give you a rundown of the architecture of Chrome, so you have an idea about the attacks. The same origin policy I assume everyone knows about. Just in case, let me explain it. This is the security policy implemented by browsers since the dawn of time. In origin, with a scheme, a domain, and a port. And it prevents a script that is executed in origin A accessing origin 2. Or origin B. And the main problem with this is that this is a very restrictive policy. So developers wanted to do more complex things in the internet, so they wanted additional functionalities. Specifications, APIs, the ecosystem gets bigger and bigger, and that means a much larger surface for attacks, in turn leading to failure, mistakes, errors. We have overlaps between different technologies, and we have new vulnerabilities, as you can imagine. This is what justified moving to a multiprocess architecture. The main benefit with Chrome is that, unlike the other browsers at that time, which had a monolithic architecture with just one huge process, they said, okay, let's start from scratch and do it the right way, first time round. What are the main benefits of a multiprocess architecture like that in Chrome? Well, they have a main process, the host process or the browser process, and then they have smaller processes, renderer processes. Ideally, each origin or each web application is executed in an isolated way in a different process. We are isolating each website. That adds security because these processes are sandboxed. Renderers would not have access to system APIs. Only the host process would have access. When the renderer process wants to access the network to see what the user is doing or to see the file system, it has to communicate with the host process. When people say sandbox in Chrome, they usually mean this. And then we have better fault tolerance. If we have one single process and for whatever reason, one tab crashes, that's it. Everything crashes. When we have a problem with Chrome and a tab has a problem, we don't lose the other tabs. In Chrome, each and every process has a lot of threads. Here I have included only the main ones, which are the ones we should be interested in. In the case of the browser process, we have the main thread, which is the point of entry for all user actions. User actions are hardware events, and entry into the browser goes through this process. And then the input-output thread of the host process, which is the one in charge of communication between processes, and also of handling access to the network, the file system, and so on. In the case of renderers, the main thread is where the most important thing happens. JavaScript is executed here, rendering pages, style. The input-output thread of renderers is the one that is used to communicate with the host process. So all messages to request a privileged action will go through the input-output thread. The other one we're not interested in, the compositor thread. Each one of these threads implements an event loop of like the ones we saw before. So communication between threads and processes is therefore message delivery between event loops. To make you see for yourselves, I'm sure you know this, in Chrome, if you go to Preferences, we have a really beautiful task manager where we can see all processes. We see that the host process, can you see it from the back? Anyway, each tab occupies a different processing space. Plugins are run in isolated processes. There's a special process to handle access to the GPU. But this is what would happen in an ideal world. We can isolate completely all origins, all applications from the web that at the end of the day are running code you cannot trust, because JavaScript, it may be interpreted in the sandbox, but it is executed in your CPU after all. So, in an ideal world, we would isolate them in individual processes, but processes take up memory. In order to strike a reasonable balance between security and memory usage, which is one of the main problems with Google Chrome, you apply different policies to map these into different processes. The main policy is process per site instance, which defines a site as the registered domain, which is the TLD plus the domain you have registered, and the protocol. So any subdomain, even with different origins, will have the same site. A site instance is the sites that are connected. And connected means that a script that is being executed in a certain application has a reference pointing at another window, okay? However, there are some exceptions to this. Like, for example, when we have an iframe. When we have an iframe on a page, we don't care about the origin. From ebuild.com, we can load google.com. Both will share the same process. Why is this the case? Well, since we need to have a reference, implementing this iframe as a different process would imply an overhead in complexity to manage that communication between processes and an overhead on communication. So iframes are the exception. Then we have linked navigation. When you click on a link in a certain page and the target for that link opens a new tab, instead of refreshing it within the tab you were in, this new one has a reference to the opener tab. In that case, that tab, regardless of the origin, will keep sharing that process. And the last exception is when we go beyond the maximum number of processes for Chrome. This is defined. The maximum number is defined based on the RAM memory that is available in the system. And that is usually 32 processes for 4 gigabytes of RAM, and up to 70 when we have 8 gigabytes or more. As soon as we have that, when we open a new tab, an existing process will be reused. In the case of the host process, there is only one host process for all tabs, even the ones that are opened with anonymous browsing. all of them will go through the input-output thread for the host process, which is unique. By the way, for the site isolation project, which is a project launched by the guys over at Chromium, they've started working on this, and I'm sure we see the results throughout this year. They're basically trying to solve all of these problems with exceptions to reinforce this isolation between sites. Even though granularity in terms of isolation of processes will never be the same as the one at the logical level for the origin, because origin and site are different concepts. There are different granularities, if you like. So quickly, what we will do now is to spy on those event loops. They do resource parsing, style calculation, layout, painting, JavaScript execution. And the most important thing here for this event loop is that every time we execute a JavaScript function, that function, as it is being executed, it blocks the entire event loop. When you go for while equals 1, this is a task that calls V8. It starts executing it, and the event loop is blocked. So you see this, the tab frozen because nothing is happening. There's no style calculation, no layout, no rendering, nothing. So depending on the length of the JavaScript they're using, it will get blocked for a shorter or a longer period of time. Main problem here, when two renderers are sharing the same process, the main thread is also shared, and the same bit of event loop is shared. The input-output thread for the host process is another event loop we'll be spying on. And I'll give you a couple of examples to explain how it works. On the one hand, we said that this is the entry point for user actions. So in the main thread for the host process, we get a click from the user, and that click from the user will go into the input-output thread of the host process, which will do multiplexing and send it to the renderer, which is in the foreground, only to the tab that is active now. The rest don't need to know about this because this is irrelevant information for them. And then we have the opposite example, which is a renderer executing a request. What it does, I can't see anything without my glasses, but thank you, Roman. If I don't see it, it is not illegal. From the main thread, we want to do a network request, okay? So we go to the input-output thread for the renderer. This renderer will send a request to the input-output thread for the host process, and this, in turn, since it wants to do something that blocks everything else, will delegate the task into a worker, which is a pool of sockets or threads that the process has to do network requests. As soon as it is done, it will say that it has completed everything in the event loop, in the input-output thread for the host process, and will send the signal to the renderer telling it that it has completed the task. That means that there will be a message in the main thread for the renderer process, which will trigger the callback to that request. I'll focus on those ones, but the idea is that these event loops are widely used. The GUI for the GPU process is another event loop. Workers, shared and service workers, work through an event loop. APIs and extensions, well, it's the same thing. And to show you that this is all true, I think I have enough time. I'll show you something. I'll show you a tool which is in Chrome by default. You probably know about it. I'll zoom in. This is the profiler. So I have a very simple page. I've just defined the listener for whenever someone does click, an alert is shown. The alert blocks the execution of JavaScript. A big signal in the event loop, which is what we want to watch. So we click here. There's many options so that we can do tracing in different ways. We click, we move the mouse, enough. Right, this is it. This is what is generated by the trace. Here we have all the processes in the browser. This is a host process. And here we have all the threads in the host process. We have the main thread, we have the input-output thread. And around here we have the renderer, which is basically the page that we have executed. Again, we have different threads, the main thread included. To show you that this is true, at first it feels weird, but it moves this way, so it's quite funny. Here we see a set of blocks. These are executions. This is a frame graph where we see all the internal calls produced by each event. If you click on them, you will see a link to the code where that function can be found. And you see that in the main thread, we're getting the signal. This is mouse displacements. This is sent to the input-output thread, and the input-output thread sends it to the renderer. You see this here? This is what the mouse displacement cursor does without any JavaScript. We have functions that are executed and block that event loop for approximately half of a millisecond. Quite peculiar cursor displacements, because the periodicity is 8 milliseconds. And here we see that a click got in. It gets to the input-output thread for the renderer, and then the callback is executed. The alert we have executed, we see the flame graph. Here we see the event handler for JavaScript. We're invoking V8, which is the JavaScript engine for Chrome. We executed the function. The function took 1.5 seconds. This is to give you an idea. This is a simplification of everything, but this is what is actually happening in the browser. An alert and a function blocking the event loop. Sorry, that was a spoiler. That was a bit of a theory. Let us move on to certain practical scenarios where it would be interesting to do things, or where people could spy on those event loops. I think the most likely scenario would be malicious advertisements. On many occasions, advertisements are loaded into iframes because the SOP protects us from malicious advertisements. It will not be able to steal the content on the page, but because this is an iframe and we're sharing the event loop, the code that executed by this advertisement can monitor whatever is happening. As we will see, this can disclose information about what the user is doing and other things. A covered channel as well, keyloggers. I will not go into the details, I don't have the time. But the main question is, how can we post tasks from a website using JavaScript, tasks into the loops? In the renderer's main thread, that's where we execute JavaScript. In JavaScript, when you execute a function, you see that a task is created that blocks the event loop while it is being processed. When that function calls another function, that happens in a synchronized way. No new task is created. It is added to the call stack. If we call a lot of functions or there is a loop, we will have a single task which gets huge, and we don't want that. We want to have a large number of separate tasks so that those we want to spy on get in between. So it's non-synchronous calls. That's the solution. What most developers use is timeout. The idea is to have an operation that is taking a long time, blocking the event loop for more than 16 milliseconds. Well, you split up in small portions, you do a timeout, and in between you can re-render the page, and the user doesn't have any feeling that this is getting frozen. The problem with timeout is that even resolution, even if you use 0.1 milliseconds, you've got problems. So resolution is not enough. And then with non-active tabs, timeout goes all the way up to 1 second. So no way. The solution is to use the API from PostMessage, which allows us to post messages in our event loop recursively. I'll show you the code. Posting a large number of tasks to measure time. Now with the new scripts, there are many more. With ES7, we have other options. With the input-output thread, we have two techniques. One, we force a network request, which will go to the input-output thread. When it comes back, we measure the time. These 5 lines of JavaScript are all that is needed to monitor the event loop. It is incredibly simple. We define a loop function. Self is a reference to our window, so we send any message. We're not interested in the content. We save the timestamp. Performance now is an API that gives you an accuracy of microseconds in the timestamp, and then we define the event handler for all messages and send the first message. Once we do that, what we have is a very short function which stores a timestamp which is executed in a non-synchronous way many times. These are tasks in the event loop. What we will have at the end is a vector of timestamps. We subtract them if they're consecutive, and we have the timestamp between 2 events. The trick, instead of using a normal array, because of the way this is implemented in Chrome, that would generate a lot of garbage collection. We would use a large typed array, and it would make it quicker. In the case of spying on shared event loops in the input-output thread for the host process, this is an example. The idea is the same as before. We store the timestamp. What we do is send a network request with a non-routable IP. When it gets to the input-output thread, it says, no, this is an error. It gives us an error message. We measure, and we cache the error so that it invokes the function again. A bit more noise, a bit more latency, because we're communicating between processes, and the input-output thread is sending it to a worker. It's a bit slower, but it gives us a resolution of some 500 microseconds. We can do it better with the shared workers. This is like a thread of JavaScript that is executed detached from the rendering. And the idea is that all communication with the shared workers goes through the input-output thread. In that case, we would have the spying website, the host process, and the shared worker. What we do is define a shared worker, which is simply responding to all messages, getting to it. The spying website has a function which is equivalent to the one we saw at the beginning. It stores the timestamp, it sends a message. The message is returned because that's what the shared worker does, and we do it again. Okay, so we save another timestamp. The timestamp we're saving now is the runtime trip through the input-output thread for the host process until the shared worker is reached. A little bit more noise, but it gives us an accuracy of 100 microseconds. If the input-output thread is congested, we will see delays in the trace that we generate. This could improve if instead of saving timestamps on one side, we save them on both sides, on the shared worker and the spying website. And then we match them. This is the idea. With that very simple JavaScript that can be executed in a website, we would generate an event delay traces. In 1 second, we will have some 40,000 time measurements. Main problems, we have lots of noise because JavaScript is very noisy. It does just-in-time compilation, it does garbage collection. In JIT, functions are optimized after a certain time. This has been executed a number of times, so we assume that next time it will be this way. If you take a look at the traces, you will see the effect of JIT compilation. At first, the function is very slow, but in very little time, it gets optimized and it's much quicker. The garbage collection part, it is non-deterministic, and the problem is that this is executed in between the other JavaScript, and that can introduce delays. Thread interleaving, well, a finite number of cores, introducing noise during the time they use CPU. And now I'll show you the 3 proofs of concept that I've put together. Very simple. The first one is basically a web page identification through these traces. I measured the event loop as a website opens in a new tab, and then based on a trace, I try to determine what website that was. And the keystroke timing information, thank you very much.
Esto
in the keystroke time information. So the idea here is to detect keystrokes. And because we cannot detect the key that has been stroked, so we just detect the time when the key was struck. Therefore, we know what happens, and therefore this reduces the entropy of the password. So we can reduce, as I say, password entropy. And in the worst case scenario, you get to see the length of the password. So this is the view of these trays of event relays. So they have been recorded for 5 seconds. So we can see that they are quite different. They are quite different. When I came here, I hadn't done any machine learning before, haven't used any machine learning, and I tell you what I did. Basically, 2 things came to mind for me to approach this topic. First of all, was using what is most classic, which is just feature extraction, and also using support vector machine and dynamic time wrapping. The idea of the first one is that you have any trace of encoded traffic or time event delays, and here you try to generate a vector for each feature where you go and say, we have sent out this amount of packages in one direction, or also the time that it takes for these packages to come and go. So we need to have an expert. We need an expert to analyze all these traces manually and to then become features. And then support vector machine. Well, I'm not going to go into that, but for you to have a feel. If we have a vector with 2 features, that is translated into a plane. We train it with many of data that we have, and then support vector machine, we try to generate a model that would tell us about the line that separates the 2 clusters of the different elements. And then the other approach is dynamic time wrapping. This is the one that I chose. The main advantage of this one is that we don't need very many samples to deliver the model, to train the models. So we have time series as well. Here, this allows us to see the vectors of our traces. We see them in the form of time series. So these are measures of delays. And instead of calculating the distance, helping us measuring the difference between 2 time series, what we do, we want to measure the difference between the 2 time series. In the case Euclidean distance, we will take the first element, that is to say 0 elements of series A and B. We will just subtract it. We sum all the differences. We move the square roots and the index at the same time, and that gives us a distance. If the distance is small, we say, well, this is similar, and if the distance is large, it's not that similar. However, if we have a trace where an event and the time when it occurs varies, the moment the trace is kind of moved, we are comparing apples with oranges. This is what time wrap does. It finds the optimal alignment between 2 traces, and then it measures, it calculates the distance. The problem, well, computationally speaking, this is a bit costly. With dynamic programming, you can do that in quadratic time. And to make it more efficient, you may establish lower bounds to make it faster and to find an optimal solution. So the solution ends up being here. Here we see the trace of event delays generated by Google.com. Therefore, I am monitoring that. Then this is uploaded in a different Google.com tab, and then I generate the trace, and also the YouTube.com. The matrix in the middle is drawing the warping path, and this is the alignment between the 2 traces. If warping path moves diagonally, means that we are aligning many Google points with one with a single point of YouTube. Okay, this is the intuition, our field. And if it moves vertically, this is the other way around. So several YouTube points are being aligned with a single point in Google. So in the end, I ran a number of experiments to see whether this worked or not. I took 500 sites, I extracted several traces. So I used a couple of different machines with different OSs. And what I did was the following. I used one single trace of each page as a reference. This is machine learning with a single sample. I'm just using a trace of each page. And if you give me traces that I've never seen before, I compute the dynamic time distance with each of the points, and I just take the closest, the nearest point. And these are some of the results. These are basically the parameters. If you're interested in that read the paper. So with the best parameters, if we use only 1 second, if we monitor for only 1 second, we get up to 62% success rates. If we use 2 seconds, that goes up to 75, and in between 2 and 4 seconds, the rate is more or less the same. This makes sense because most of the sites after 2 seconds, they just do whatever they are expected to do. I'm not going to go into cross-validation. These are the results of the experiments that I ran. And now, inter-keystroke timing information. That's the other proof of concept that I did. We've seen that the mouse displacement, scrolling, clicks, are all translated into a JavaScript blocking that event loop. And usually the patterns that are generated because of their different periodicity or shape or length allow us to identify them. How am I doing with time, Roman? 10 minutes to go. Basically, this is the output of a tool that I'll show you later on. It is an HTML page drawing graphs. And basically, this square box is the zoom of the trace that we generated, and we can see whether each of these peaks matches the movement displacement of the profiler. When we use a Google profiler to understand things, that's very nice. However, you cannot use that later on to see how long it takes for an event in real world, because the profiler is introducing lots of the code that is executed in the middle. So therefore, the performance is seriously impacted. So it says this is more or less 1 milliseconds delay. Separation is 8, so we see all these peaks in blue. So if you see this trace, you go and say, well, the user is displacing his mouse. And then, well, the same goes for clicks, if you want to focus on clicks. So this is what you will see if there are no event list defined in JavaScript to listen any events. But if a page defines several events, well, the pattern of each event will look differently. Therefore, I did the following. I looked at the aspect or the look of the pattern of a keystroke in Google. So we see 2 consecutive events, the key down and the key press. So we go back to element inspectors. So when the user strikes key, a JavaScript function will be executed. Every time you strike the key, JavaScript blocking the event loop. And this is what we are seeing here. So what was my experiment about? I took several passwords, and then I set up element emulating the victim. It skipped the pop-up of Google Logout, which is a typical event because the pop-up has a reference and shared events. The site, the web page can spy on it, and I introduce a keystroke with a delay between keys of between 100 and 300 milliseconds. And on the one hand, I got the information of Selenium that timestamp tells me, and then I also get the timestamps that I identify with my super elaborated technique of machine learning to recognize patterns of keystroke. And then this is the technique that I use. I use this piece of JavaScript, and if I go through the trace that a user creates as he writes, and by looking to consecutive events within that range between 100 and 300 milliseconds, I get a success rate of 91%. So therefore, in 90% of the cases, I detect the length of the password as well as the millisecond where each of the keys has been pressed. I know that I'm going fast. And now I'd like to show you cover channel that I implemented a few days ago. Basically, we have two different processes. One of them is sending silly requests to monitor the event loop, and the other one is sending out lots of noise. If noise is above a specific threshold, we get either 1, and if it is below the threshold, we receive a 0. This is a proof of concept, very simple to implement. You could implement it more carefully, and if so, we do. Well, a scenario that comes to mind, for instance, imagine that you have a tab doing weird things in a weird domain. If you filter it, and if someone is looking at that, in the dev tools, you can see that that is making connections outside. If you wait for the user to open less weird service, you use that cover channel, and then from a domain that looks harmless, you can use it to send something out. So if you like cover channels, well, we'll upload this one together with others on the GitHub. These are good fun. And I'm nearly finishing now. Loop scan. This is what I did. Take a look at the graphs. Well, first of all, to draw the graphs and to understand the traces. You want to see a site, to do things there, and to see how all that is translated. You say, okay, in this page I'm doing this, and this generates a super trace that I can easily identify. And this tool helps you do so. Okay, so I started. This is the trace has been generated after spying on the input-output thread of the host process. And as I told you before about the optimization before, is shown there. We can displace ourselves here, there, zoom in, zoom out. So this is the mouse displacement. I've monitored that as I was doing nothing, but if we repeat the process now, I open a tab. So this is very slow. We see more activity, more things taking place here. Not very many things, but this is for you to have a feel about it. And in the case of rendering, this is even clearer because there is less noise. So the thing is that I have to clean this up. I will publish it very soon. So this is very simple. You've seen the JavaScript code, and I use it for quick viewing. I just didn't want it to be nice. I just wanted it to help me identify patterns. Well, and if you want to create a logo, feel free to do it. And then countermeasures. One of them could be limiting the rate at which tasks can be posted. And if you do that, what happens? You are just crashing or ruining the streaming of web pages. It has a huge impact on performance. The other one could be reducing the performance of timestamps. That is to say, so that you cannot see that at microseconds, but at a higher time or rate. So there are different possible ways to measure times, not only in milliseconds, but also in nanoseconds. You can do that with your browser. So you can use, make a silly loop, and then starting a counter, and every time. So when you finish the request, you just take a look at the counter, and that is a pseudo tick, and it shows a pseudo check of execution. There are many ways to do that. You can either reduce the resolution, well, reducing the resolution of APIs to measure times is not a good solution, it's useless. And now full isolation. The problem with that is granularity of isolation. So if you compromise a subdomain, or if there is a subdomain that you don't fully trust in terms of likeliness of it executing malicious code, well, the issue of the host process continues to be there, or the extension, the plugins, that does not fall within the site isolation projects. And this is something that happened to me when I finished running my experiments, and then out of the sudden, my laptop upgraded to the latest Chrome. And the thing is that they have implemented the CPU throttling. So it means that when you have it up in the background, the use of the CPU is limited. And I didn't like that, because that was a problem for me. But, well, people started to complain about that. Because, for instance, you are on Spotify, you are listening to music, and you have it in the background tab, then the music stops playing. And developers said, look, if the API is in the background, and if they use the audio API, let us put it in the foreground. If you do that, you bypass that. So it had an impact on me. However, there are different ways to bypass that. So the conclusion is, as it's been said before. So if you find an exploit in Chrome, that is parched, and that's it. Any logical failure can be easily patched. However, with iChannels, they are very difficult to mitigate, because security is the only factor of Chrome that requires to have usability, not to take up lots of memory. They have to run fast, so you really need to find intermediate points so that everyone is happy and secure. I'm nearly finishing. Future, other browsers? Well, as I said, Firefox is moving towards multiplex, which is different architecture from that of Chrome, but without taking a look at the architecture details, using loop scan, you can see a similar situation with the loop events. So the problem is there with other browsers. Therefore, I have curiosity. I'm curious to see what will happen with Servo. It is a new engine being made in Rust. I want to see how event loops are processed there. And as I say, I was curious about it. And also improving attacks. These are proofs of concept, covered channel, identification of websites. I use only one trace to learn. If you use more traces, performance goes up a lot. And then event loops is very generic. It's not only exclusive of browsers, so we have to see what other environments event loops are found. And we have to see whether we can monitor them as well. So thank you very much for your attention. So we are doing good with time. So we have time for two questions. I have a question. And what about doing the typical add-on, the typical plugin that you can have it in a OpenTab, so that it's running there, so that it is creating noise? Well, many people ask me just the opposite. I say, what happens if you introduce a scenario of malicious plugin always running? Well, actually, you can do fingerprinting to malicious plugin and to detect them when they are used, to detect them through event loop. Yes, you could do that. Any other questions? All right, thank you very much, Pepe. I remind you that you can cast your vote in Kauri